Hi, my name is Dr. Matt Moynihan, and I've been involved in fusion since 2006. I'm releasing this series of lectures on YouTube about the history of nuclear fusion research, and it's built around my book, An Insider's View of Commercial Nuclear Fusion, which I highly recommend you get. It's available on my website or on Amazon, and we have a new version coming out next year with Nature Spring, or actually maybe this year. This is publicly released to the general population as a way to explain nuclear fusion to most people who don't know anything about it. I'm doing this as a public service because I believe that nuclear fusion is not getting the attention or the funding or support that it needs from the federal government or governments around the world for that matter. And it's not happening fast enough for us to have an impact on the worst effects of climate change. So I've made this 10-part lecture series as a way to get general information in the hands of the general public, politicians, military leaders, investors, and other fusioneers inside national laboratories, universities, and other places. If you want to learn more, you should consider buying a copy of my book, which has a more complete definition of everything that's going to be discussed in this lecture series. So before you check it out, I want to give you some disclaimers. This was made by me recording verbally things from memory that I had written down in my book. And there are 10 parts in this series. There's an introductory chapter, a chapter on modeling. Then we go pinches, mirrors, custs, inertial electrostatic, ICF or laser fusion, tokamaks and stellarators, PGMIF, and plasma structures. So 10 chapters covering 10 different topics. Now, the accuracy is me from memory. So there are mistakes. It is not perfect. It is about as accurate as Wikipedia, maybe a little less accurate than Wikipedia, but it does provide a rough overview of the entire field from a new perspective from someone who's been studying this for about 15 years. Where possible, where there were mistakes, I tried to put in corrections. So if you verbally hear something and it's wrong, you may see something flash across the screen stating correction. This name was wrong, or the date was wrong, or the year was wrong, or I had little amounts wrong, things like that. So there are mistakes. It is not perfect, and I invite folks from the fusion community to provide comments. But however, a lot of people in the fusion world, the private fusion world, and the public fusion world have been talking about a general education training course, and there's committee meetings about this. I thought I could just put this out quickly and help educate the general population about nuclear fusion. Fusion is really important. If you care about climate change, if you care about melting glaciers, if you want to stop carbon production, this is the kind of Hail Mary, game-changing technology that would really make an impact. And it's got a long, rich history, over 70 years. Lots of different approaches have been tried. There's a lot of people that were involved. This lecture series and the book, really the book, celebrates the history, celebrates some professional work, and it really helps you get oriented to the field. So I really hope you enjoy this series. Please reach out if you have any questions. Hope you take care and check it out. All right. Have a great day.
Hello, folks. This is an intro lecture on fusion technology as part of a series of lectures around different families of fusion approaches and organized around the content of my book, which I recommend is available for purchase online. I recommend you get a copy if you're interested in learning more about nuclear fusion. So, just general overview. Fission is where you take a big atom and split it apart. Fusion is where you take two little atoms and put them together. Technically, it's two hydrogen atoms, which are the smallest atoms and the ones that we know how to fuse. You have to get them within 2 femtometers. That's 2 to the negative, I think, 16th. To get the quantum tunneling effect, which causes their nucleuses to bind together. And when that happens, some of the binding energy is actually lost. It's some of the binding mass. You can think of it like the glue that glues a nucleus together in the form of mass actually gets converted into energy through E = mc squared. So that's the basic process of fusion. Theoretically, you can fuse any two atoms in the universe if you had enough energy and density and force behind it. You could fuse any two. In practice, though, there are three different options. There's deuterium, tritium, and proton boron 11. Deuterium is the simplest one. Deuterium gas is a fuel, is available online. You can buy a cylinder of it for $600. You can get a $600. You can get a 5-foot tall cylinder with maybe a 95% quality purity, and it can be bought through websites like Specialty Gases in Las Vegas. And it's the fuel of amateur fusioneers and people who build fusers. See the IEC lecture, excuse me. Then you can throw tritium in the mix. Now, tritium is more expensive. It's radioactive. It has a 12.5-year half-life, which means that as soon as you start to buy it or stockpile it, it starts degrading immediately. I tell people that if you're throwing tritium into your reactor, you're getting about a 15 to 20x improvement in reactivity, or I guess fusion power output. So it's a boost to your reactor performance by a factor of about 15 to 20 in terms of the amount of energy that you're making per unit of volume. But it comes with commensurate problems. It's OSHA regulated, EPA regulated, NRC regulated material. So at least in the United States, you're spending on the order of $20 million over a 4-year period to set up a small tritium handling facility to do, say, under a gram of the stuff. And those numbers are rough, though, but they're kind of a good rule of thumb. So if you have a gram of tritium in your reactor system, $20 million for 4 to 5 years, a team of 24 folks to build the entire handling system around tritium, tritium processing, and then monitoring for tritium releases, and then dealing with the regulatory stuff, the OSHA, EPA, NRC regulation framework. So as you go up in the amount of tritium, you go up in costs. A kilogram of tritium, you're talking hundreds of millions of dollars for a handling system, a treatment system, a monitoring system, and certifications to handle the stuff. Most fusion reactors want to breed the tritium using a lead lithium blanket so that the neutrons coming off the fusing plasma would then lead to a tritium reaction, which then you could recover the fuel and handle it. Right now, the stockpile of tritium comes nationally from the Savannah River site. It's a DOE-produced material. It's used for fusion bombs, and a lot of that capability is just at Savannah River. And Savannah River, by the way, is scaling up. They're hiring thousands of people this year. So if you want to tap that kind of expertise, that's a good place to go. Another place is the National Ignition Facility has tritium handling, and the Omega laser system at the University of Rochester has tritium handling expertise. So that's a good place to go. And then, of course, the third fuel combination, we just talked about deuterium, tritium, is proton boron 11. Now, that's the dream for some companies because it's aneutronic, aka it does not make radioactive material directly, although there is a branch reaction in the proton boron system that produces a small, like under 5%, maybe more closer to 1%, radioactive material. So proton boron 11 is often promoted as this dream fuel that will produce fusion energy and power with no radioactive waste, but that's not true. It produces a small amount of radioactive waste. That's the first thing. And the second thing is that it's about 15 times hotter to get the same reactivity that you would for deuterium and tritium. So you got to go about 15 times hotter to make that plasma work. And that's a problem. That's the kind of thing that most people in the fusion research community says 15 times hotter is just, it's too hot for our blood. That's too difficult for our machine. That's too hard for our reactor. That's a reach fuel. That's a dream fuel. That's an advanced fuel. That's something that's just not going to happen in the next 20 to 30 years. And I get questions about this all the time. I'll tell you point blank that I don't really care what kind of fuel you put in your fusion reactor. I don't care if it's deuterium, tritium, or proton boron 11 or something else that people have proposed. What matters to me is how your reactor is designed. What is the design of your machine, and how does it make it? What makes it special? What makes it unique? What makes it work better than something else? What's the trick that you're using? What's the innovation that you have, either engineering, plasma, or something else that's going to make it work better? So again, it doesn't really matter. A fuel discussion is something everybody gets into at the beginning when they're just learning fusion. But once you've been in fusion for a while, you realize it really doesn't matter what kind of fuel they're using. It's more about the other aspects of their pitch that make the difference. So that's a good summary of fuel and fusion itself. Fusion as a power plant was first sort of spelled out in the 1950s. And one of the seminal papers on this topic was written by John Lawson, who was a British electrical engineer. He was eventually knighted, so you call him Sir John Lawson because he was knighted for this work. But he was an engineer, and he was imagining what a fusion power plant would look like back in the day when we were first messing with the idea of a fusion power plant, back when pinches were pretty much the dominant concept. And he envisioned the sun in a building. That was his first conception of this. So if you think about the sun, it's a big ball of plasma that's dense and hot in the sky, and it's compressing material to temperature and pressures where fusion occurs. Now, the sun loses energy through two mechanisms. One, radiation losses. That's light. That's light leaving the sun in all forms: X-ray, UV, IR, visible, and anything else that's bleeding energy away from the sun. That's a loss mechanism. And that's a major way that a fusing plasma or a fusion reactor would lose energy. As light leaves the plasma, it takes energy away with it. So anything that uses a plasma is going to be subject to that radiation loss. So that was his first observation. His second observation was the loss of mass. That's any particle, be it an ion, electron, neutron, atom, half-fused atom, hydrogen, helium, anything with mass at all that's leaving the plasma is taking energy away with it in the form of thermal heat. And he called that conduction losses. So radiation losses, conduction losses. In the context of a power plant, that's anytime plasma touches a wall, any surface, any metal surface, any magnet, any diagnostic, anywhere that a particle touches a piece of metal and is conducted away is a conduction loss, and that's a loss of energy. There's also the way the machine produces energy, the fusion energy generation term. And in the case of the sun, that's how many fusion reactions per second, how many atoms are squeezed together and creating fusion or doing fusion. And it's a function of the temperature, the density, and the amount of time that the thing is held together. And it's also a function of what you're fusing. So if you change fuels, fuel A and B might have a great fusibility coefficient. Fuel B and C might have a terrible one. Fuel D and E might have a great one or a terrible one at certain conditions, but not at other conditions, this sort of thing. All of that information is boiled into a term called the cross-section, the nuclear fusion cross-section. Now, cross-sections were measured extensively in the 70s and 60s in particle accelerators. The United States really did fund a lot of this work, and it was all around weapons research at the time. But the way they did it was they had hundreds of experiments where they would take object A, which might be, let's say, a block of lead or a block of gold or a block of water or ice or whatever, and they fired particle B at it. So particle B might be a neutron, might be a hydrogen ion, might be a helium ion, might be a lithium ion. And you go through all these different configurations and iterations and temperature and energy spreads to basically map out the cross-section for any two atoms that are interacting. And they create quite a large database of all this data, which is, as you can imagine, tens of thousands of experiments over 20 years of work at all these different particle accelerators. This all gets combined and loaded into the Los Alamos TF2 database, which is available. You can actually access through a web portal. A lot of that data also ends up in modeling software today. So today, this is really easy. You pull up a library of materials and you say, I want to look at, plasma A interacting with the wall that's made of tungsten. And it's going to come off between this energy and this energy. What's my cross section? And it'll just spit it out. So this kind of warehousing of data is a huge accomplishment for the United States. And in any case, that term plays into the fusion energy generation term. And it also is, by the way, should mention, dependent upon how the collision occurs. So if atom A and B slam together head on, they have the maximum collision energy, and that probably improves the cross-section and the odds that they're going to fuse together. If they have a glancing blow and they hit at some weird angle, then they're less likely to fuse together. And you got the math and model kind of accounts for all these random interactions sort of mathematically, and it kind of does the statistical average of all that stuff. But anyway, fusion rate equals the cross-section times the density of A, the density of B, all together as one term. And that's the fusion energy generation term. So just to review, we've gone over 3 terms now. Fusion energy, the amount of energy made, the conduction loss, the radiation loss. And these 3 things are going to be in Lawson's energy balance. And implicit in that fusion energy generation term is density, time, temperature, which is also known as the triple product or the Lawson criteria. These are all terms that people kind of use ad hoc in the fusion space. So it's good to know all the terminology, so when you're having a conversation with somebody about all this stuff, you understand what they're talking about. Now, Lawson's 4th term is efficiency. Fusion energy minus radiation minus conduction all times efficiency. And efficiency applies here because we're not talking about the sun, we're talking about a power plant, and a power plant has efficiency. And so, and that includes things that go into that term are things like better magnets, better wire, better designs, more efficient reactors, more compact spaces, better energy capture, better energy recovery. All of these innovations play into improving the overall efficiency of the fusion approach. Things like better laser systems, more efficient laser systems that couple better to targets. All of these innovations, again, play into that efficiency term. So Lawson, being an engineer, comes up with this energy balance, the Lawson energy balance, and he applies it to fictitious plasma that he calls, well, he would call it the sun in a building, essentially. He says, I have this homogeneous amount of plasma, it's just like a big ball in a building. I don't really know anything about the details, about how we hold it, how we manipulate it, how we compress it, but I'm going to apply some general rules about the amount of energy that's radiated away and the amount of conduction losses, and I'll figure an efficiency of 25%. And based off of that, he derives a minimum density temperature time that he says you got to get to make net power possible. And that becomes the Lawson criteria. And over time, different authors and different scientists make assumptions about how much energy is going to be radiated off and how much conduction is going to come off. And based off that, they try to predict what the minimum conditions are for a fusion power plant. Over the last 70 years, since the 1950s till today, I think the fusion research community has put so much emphasis on triple product that they've ignored lots of other important factors that you would think about when you were building a power plant, right? So things like the magnets, or things like more efficient designs, or making a more efficient driver, or other things. It just became, hey, let's get the highest triple product possible, and let's ignore all these other things like cost, or size of power plant, or the amount of concrete that we use, or things like that. And in the last probably 15 years, as the fusion community has moved from a university academic government laboratory type endeavor to a privately funded kind of thing, these considerations have sort of come back in. Anyway, I often explain fusion approaches through the lens of the energy balance system, because when you look at an innovation, and I'll just pick one, like the Lockheed Martin's compact fusion reactor was all about reducing conduction losses because they had a really innovative magnet design that lowered the conduction losses. The PFRC, the Princeton Field Reverse Configuration, has a really innovative way to heat and stabilize the plasma. And because they form a structure there, see this lecture later, they are keeping the material in one place, and they're also reducing conduction losses. In other places where you see like folks that'll design a reactor and they'll put lots of space around the plasma, or they'll try to hold it better with better containing magnetic fields. Again, they're trying to put space between to lower conduction losses. So if you look at these approaches through that lens, you can kind of get a lot of, tease out a lot of interesting details. So we've talked about the energy balance. We've talked about the fuel approaches. There are a family of technologies that we're going to talk about in this lecture series. It might be worth it to go through each one briefly. So there's a thing called the pinch. That's going to be the first chapter because the pinches were the first machine that worked that was not an atomic bomb. And that's relevant today because there are flowing pinch companies in play right now, including one called Zap Energy in Seattle, Washington, and the company called Fuse in Montreal, Canada, is following also a flowing pinch approach. There's an approach called mirrors, which was evolved in the late 1960s with Dick Post in the early 1970s, and received a largest amount of U.S. funding from 1972 to 1986, roughly. Mirror approaches reflect plasma in a line, and so plasma bounces back and forth between two magnetic mirror coils, and they collide in the center, hopefully do nuclear fusion. Mirrors have a number of problems, but that's going to be discussed in the mirror lecture. There is a plasma structure lecture, which is all about different ways that you can create quasi-stable, semi-stable smoke ring type structures out of plasma. Plasma is a fluid that conducts electricity, which gives it this unique property where if you get current going in that plasma, that current's going to create a magnetic field about 90 degrees to it. Same way that an electromagnet creates a magnetic field, or current in a wire would create a magnetic field. So it has a unique property that it does that. So we're going to talk about that. There's going to be a chapter on tokamaks and stellarators and spherical tokamaks, which are the worldwide heavyweight in nuclear fusion. Over 215 tokamaks have been built, planned, or decommissioned around the world, and probably the leading candidate for a fusion reactor. And there's going to be some lead into the private fusion efforts around tokamaks, aka Commonwealth and Tokamak Energy, and some of the superconducting technology that's going to enable that. We'll talk about ICF. We'll talk about the history of ICF. ICF is a rich technical program. Although it was a weapons program, and it really is a weapons program, everyone in the ICF community always hoped that they would take it to a fusion program. And with the recent announcement from the National Ignition Facility of ignition, essentially, now the community is coming together to write the first inertial fusion energy plan, national plan, IFE plan, that they hope will foster more funding from the federal government into developing that. And I want to talk about some of the limitations of ICF. And there's also some commercial players in ICF, like First Light Fusion, that I'm going to talk about in that lecture. There's also PJMIF, Plasma Jet Magneto-Inertial Fusion, which gets its own category because it's sort of unique. It's a hybrid between ICF and tokamaks, so we're going to talk about that. We're going to talk about CUS systems. Most famous CUS system is the Lockheed Martin Compact Fusion Reactor. And we're going to talk about IEC, fusers, which is a great technology for high school students and hobbyists that are interested in learning more about fusion. So if you're keeping track, that's like 6 or 7 lectures. I'm going to do a modeling chapter also, and I'm going to do, I think that's I think that's every one of them. Hope you really enjoy the lecture series. Give me feedbacks in the comments. Want to hear what you think about all this. And again, this is ad hoc, off the cuff kind of talking. So it's as accurate as Wikipedia. It's mostly accurate, not perfect. We're going to try to add asterisks and little edits here and there when things are spoken wrong. I want to talk a little bit also about Spinoff Technologies and other applications for fusion, because there's a number of exciting ones. Right now, today, commercially, you can buy nuclear fusion machines that do nuclear fusion. And the most famous example of that is Shine Medical Technologies, which is a company in Janesville, Wisconsin, that was founded in 2010. It was founded after Phoenix Nuclear Labs, which is really the older company, which was founded in 2005. Both these companies are developing neutron generators that use fusion to generate neutrons, and then apply those neutrons to things like medical isotopes, neutron imaging, and other spin-off applications. Medical isotopes, by the way, is the primary market, and it's a $5 to $6 billion a year market. So Shine is set up to do that. And I'm going to talk about them extensively in the IEC chapter. One of the other exciting applications is fusion rockets. You can eject a plasma that is undergoing nuclear fusion out the back of a rocket ship as the plume exhaust. So as a substitute for chemical rockets, you see the plume exhaust coming off the space shuttle. This would eject fusing plasma, which is going at some percentage of the speed of light. So as the plume comes out the back of the ship, it exits at some percentage of the speed of light. That imparts momentum, so mv, so mass times velocity, a vector, to the ship going in the opposite direction. And so, but there's a trade-off there because the mass of the plasma is very, very, very low against the mass of the ship. So it's providing a little bit of supporting force with each exhaust puff. High velocity but low mass. So if you're plotting the speed of the ship, it's increasing exponentially. It's sort of on an upward exponential trend, and then when you get to your halfway point between your destinations, you actually turn the thing off, turn the ship around 180 degrees, and shoot it off in the new direction. That slows your ship down. And so that approach for fusion rockets can get you to Mars in like 90 to 120 days. Round trip. You can get to Mars in 30 days, and then you can spend a month on Mars, and then you can come back in like 50 to 60 days. So 100 in total, 100 and change round trip to Mars using this fusion thruster approach. Which is an exciting spin-off technology for fusion. I think one of the most exciting in this menagerie of spin-off technologies, because it allows us to get to a whole new planet, and it opens up an entirely new market for raw materials and other things. There are 4 companies that are chasing fusion rocket technology that I'm going to talk about in the lecture series, but I'll just briefly mention them now. There's one called Helicity Space. They're a Berkeley, California-based startup that were formed by a merger between a PhD from the academia that had worked on plasma jets and a fellow from Goldman Sachs who had been a managing partner at Goldman Sachs. So they have a really innovative concept. There's also the Princeton field reverse configuration approach that's being commercialized into a fusion rocket by a company called Princeton Fusion Systems. I'm going to talk about their stuff in more detail in the plasma structure chapter. There's an approach developed by MSNW, which is a company in Seattle, Washington, which may be defunct now. But I'm going to talk about them, also the history of their work in the plasma structures chapter. There's also a team at Princeton that's looking at spinning out into a company around Fatima Ibrahimi. She's a professor at Princeton that observed a weird behavior in NSTX that can be converted into a plasma thruster. And then there's a team called Near Star Fusion, which I'm going to talk about in the PGMIF team structure or chapter, excuse me. They're a company in Chantilly, Virginia, and they have a concept for a fusion thruster. So 4 or 5 teams looking at this. They're all members of the Fusion Industry Association Committee, and they wrote a national plan to study fusion rockets over the summer of 2021. The U.S. Air Force has some interest in this, and I think it would be compelling technology for the Air Force, especially given the prominence of hypersonic missiles. This is essentially the next hypersonic type technology, and it's also faster than the hypersonic. So under certain conditions, it could be kind of game changing. And since the United States is sort of lagging behind the rest of the world in hypersonics, we can't let the same thing happen in this technology. We need to be leading the world in fusion rockets, and that's sort of the thing that the military would be interested in. There's a couple other broad stuff about fusion that you should be aware of that doesn't fit in any other chapter. Fusion benefits from magnets. About 60 to 7% of all the technologies that I'm going to talk about in this lecture series use magnets in some way to manipulate their plasma. Because if you're thinking about it, there's only a couple options here, right? You can compress your plasma with shock waves, doing some sort of compression thing, either with a rail gun or an ion beam or a laser system. It's kind of squeezing your plasma with shock waves. That's one option. Another option is you can use electric fields. Fusers use electric fields to run plasma in certain directions, or heat it, or cool it, or slam it together. Particle beams do the same thing. Some of the diagnostics and heating approaches use electric fields to heat beams of ions. In the direct conversion world, where they're doing energy recovery, they use electric fields to manipulate their plasmas. So electric fields are another option in your toolkit. You got compression, electric fields. You can also use magnetic fields, and magnetic fields are probably your best option because of the energy density in a magnetic field is just so much higher than the energy density in an electric field, which means you can hold hotter, denser, better performing plasmas in a magnetic field. Now, I want to point out that you don't need external magnets to do this. The plasma can generate its own magnetic field internally, and all the plasma structure stuff that's talked about in that lecture are essentially doing that. The plasma is flowing in a certain way, and that's generating its own internal field that's used to self-manipulate, self-structure, self-control the plasma. So magnetic fields can come from external sources. They can also come from internal sources. This is a nice distinction that I want to make. So again, let's just review. So shock waves, so physical compression, electric fields, magnetic fields, or a fourth option. So of these 4, magnetic fields have one of the best advantages, and about 70% of the approaches that I'm discussing here will use a magnetic field in some way to get what they want out of their fusion machine. And so therefore, a lot of them will then benefit from superconducting, high temperature superconducting materials. So when you have advances in the field of superconductivity with HTS wire, you will have corresponding advances in the magnetic field, which will also impact the quality, performance, and behavior of your fusion reactor concept. That's why I think, and I personally believe, that the field of superconductivity magnets and the field of nuclear fusion will be inexorably linked together going forward over the next 10 years. And we've already seen this story kind of play out in the tokamak world. Tokamak Energy was founded in 2009 with that sort of idea in mind. Commonwealth Fusion Systems, founded at MIT in 2017 with a similar sort of story. And they're also co-pitching that, hey, we can sell this wire, we can sell this HTS magnet technology pre-reactor. We can generate money pre-reactor, way before we get to net power. We can already be making money for our investors and VC community. So, but the question is, what does that do for the other approaches? What does a superconducting stellarator look like, or a spherical tokamak, or a mirror machine, or an FRC, or a PGMIF approach, or you name it, a pinch approach, or something else? When you throw this superconducting wire into the mix, all these reactors start to change. And that's, I think, a big story and the big trend in fusion right now and will be for the next 15 years. And by the way, it doesn't necessarily just apply to magnets. The HTS wire is a way to efficiently move lots of electricity from point A to point B. So it applies to the electrical power system as well. You can use the HTS in the back end power system of the reactor. So it doesn't just fit in the magnets, it fits in other parts of the whole reactor design. So that application, that technology is a really juicy spin-off of nuclear fusion research. And it's not a story that's really been told yet. What are the other applications of HTS wire that you can do with in other industries, in totally new industries like wind or solar or electric vehicles or MRI machines or weapon systems or defense applications? And that's something I think needs to, maybe in the next 5 years, we'll start to see that ripple effect. Because remember, going to the moon wasn't about necessarily getting to the moon. It was about the 20 or 30 other technologies that spun out of the Apollo program. In much the same way, getting a net power fusion reactor is probably not about that. It's about the 7 or 8 other ideas and technologies that come along the way to getting to net power. And HTS, I think, is a really good first one that could come out. Okay, I appreciate your time. I hope you enjoyed the lecture series. Take care.